Hello everyone, this is Muhammad Wasim Khan, an instructor of your Total Quality Management course. Welcome to Learn with Wasim. In the previous lecture, we have discussed statistically based quality improvement for variables. But in today's lecture, we are going to discuss statistically based quality improvement for attributes. In this chapter or in this lecture, we are going to discuss what is an attribute. We will explain the generic process for charts. We will also discuss understanding the attributes control charts. And then we will interpret those attribute control charts. And at the end, we will also discuss when and how to choose the right attribute chart. William Shakespeare says, "To be or not to be, that is the question." This quote might seem to you like an odd one for equality management. However, the quote gets at the core of what is an attribute. In supply chain quality, we are usually asking ourselves, is it a defect or not? Is the piece defective or is it not? So attribute is a peculiar and essential characteristic. Attribute is something that either does or does not exist. Customer-based attributes are more associated with customer satisfaction, whereas the production-related attributes are more internal and engineering oriented. We have 5 different types of attributes, and here we are going to discuss 4 of them. The first one is structural attribute. Structural attributes have to do with physical characteristics of a particular product or service. For example, an automobile might have electric windows. Services have structural attributes as well, such as a balcony in a hotel room. The second one is sensory attributes. It relates to sense of touch, smell, taste, vision, and sound. For products, these attributes relate to form design or packaging design to create products that are pleasing to customers. But in services, such as restaurants and hotels, atmosphere is very important to the customer experience. The third one is performance attribute. Performance attributes relate to whether or not a particular product or service performs as it is supposed to. For example, does the lawnmower engine start? Does the sound system meet a certain threshold for low distortion? The next one is temporal attributes. Temporal attribute relates to time. For example, were delivery schedules met? This often has to do with the reliability of delivery. And let's discuss the last one, which is not presented to you on the screen, but please note the 5th and the last type of attribute, and that is an ethical attribute. Ethical attributes are more important to firms. For example, do they report properly? Is their accounting transparent? Is the service provider empathetic? Is the teacher kind? or not. As you can see, all these types of attributes have to do with some state of being. These are often a binary in nature. Either the flaw exists or it does not. From a quality management point of view, we understand there is a difference between attributes that are desired by customers, attributes, and that are monitored in the production processes. As we have discussed, that we have the customer-based attributes and the production-related attributes. Customer-based attributes are more associated with the customer satisfaction, whereas the production-related attributes are more internal and engineering-oriented. Both types of attributes are important. Let's talk about the generic process for charts. As we have discussed in the previous chapter, the use of control charts. So we do not repeat control chart basics here. Attribute charts are developed and interpreted the same way as variable charts. The only difference is the statistics of interest. Previously, we dealt with measurements, and here we will deal with the states of being. To reiterate, the generic process for developing process charts consists of the following 6 steps. The first step is to identify critical operations in the process where inspection might be needed. So we have to identify the critical operations where inspection might be needed. These are the operations, the critical operations are the operations in which if the operation is performed improperly, the product will be negatively affected. That's why we call it the critical operation. The second one is to identify critical product characteristics. These are the attributes of the product that will result in either good or poor form, fit, or function for the product. And the third one is determine whether the critical product characteristic is a variable or attribute. This one is an important step. You have in the third step, we are actually differentiating between the variable and attribute. So it is very necessary to identify whether the product characteristic is a variable or attribute, because variable and attributes may have different charts, and we will discuss those charts in this lecture. We have already discussed the charts that we can use for variables, but in this chapter we will discuss the charts for attributes. The fourth step is to select the appropriate process chart from among the many types of control charts. So as we have identified and determined whether the product characteristic is a variable or attribute in step 3. In step 4, we will have to select the appropriate process chart. In step 5, we have to establish the control limits, okay, and use the chart to continually monitor and improve. Then we will have to identify that whether it is within the control limits or out of the control limit. If it is out of the control limit, we have to do some changes. We have to continuously improve it and make the process more ideal. And the sixth step is to update the limits when changes have been made to the process. So these were the 6 basic steps for developing the attribute charts. Now let's discuss understanding attributes control charts. Attribute charts deal with binomial and Poisson processes that are not measurements. We will now think in terms of defects and defectives rather than diameters and widths. As you know, diameter and widths were variables. So we are here talking about the attributes. That's why we will think in terms of defects and defectives. A defect is an irregularity or problem with a larger unit. The larger unit may contain many defects. For example, a piece of glass may contain several bubbles or scratches. Some of these may be detectable only with a magnifying glass. Defects are countable, such as 6 flaws within a particular glass pan. But defective is a unit that as a whole is not acceptable or does not meet performance requirements. For example, a letter with a wrong address is defective. Also, a letter could have several defects, but the entire unit is labeled defective if there is a single defect. Defectives are monitored using P and NP charts. Defects are monitored using C and U charts. So please note it that defects are monitored using P and NP charts, whereas defects are monitored using C and U charts. So let's discuss P chart and NP chart first, and then we will move toward the C and U charts with examples. P charts for proportion defective. The P chart is a process chart which is used to graph the proportion of items in a sample that are defective. P charts are effectively used to determine when there has been a shift in the proportion defective for a particular product or service. Typical applications of the P chart include late deliveries, incomplete orders, calls not going dial tones, accounting transaction errors, clerical errors on written forms, parts they do not mate properly, and so on. The subgroup size on a P chart is typically 50. It is between the 50 and 100 units. The subgroups may be of different sizes for a P chart. However, it is best to hold subgroup size constant. Usually, at least 25 subgroups are used to establish a P chart. The formula for P chart is presented to you on the screen, which is the control limits for P is equal to P bar. The control limits for P is equal to P bar plus minus 3 whole under the root into P bar into 1 minus P bar divided by N. Here, P bar would be the central line, and P, if we use the plus sign here, then it would be the upper control limit. And if we use minus instead of plus, then we will have the lower control limit. So P is the proportion defective, where P bar is the average proportion defective, and N is the sample size. Let's discuss an example so that you can easily understand P chart. A production manager for a tire company has inspected the number of defective tires in 5 random samples with 20 tires in each sample. The table below shows the number of defective tires in each sample of 20 tires. Calculate the control limits. So there were 5 samples, 1, 2, 3, 4, and 5, as it is mentioned here, 5 random samples with 20 tires in each sample. So 20 tires in each sample. And these are the defective in each sample. For example, in the first, as it is shown in the table, in the first sample, 20 the first sample of contain 20 tires, and while checking the 20 tires, it has the investigator or the quality engineer or inspector have inspected 20 tires, and 3 of those tires were defective. Similarly, in sample 2, out of 20 tires, 2 were defective, and so on for the remaining samples. So the total number of defective tires would be 3 plus 2 plus 1 plus 2 plus 1, which is equal to 9. And similarly, the total number of tires in sample in 5 samples is equal to 100. So what would be its proportion defective? Proportion defective mean P. So its proportion defective would be 0.15. So you can see here that 3 divided by 20 would be equal to P, which is 0.15. Similarly, the P value, which is the proportion defective for sample 2, is 2 divided by 20, which is 0.10, and so on. So let's talk about the control limit. Is in the previous slide, I told you that a CL, or the control central line, CL is a central line. So central line is equal to P bar, which is the number of defectives, that is total number of defectives, 9, divided by the total number of samples, which is 100. Okay, so the total number of defectives divided by the total number of inspected units. So that would be equal to 9 by 100, which is equal to 0.09. So the central line of the P chart would be 0.09. Now sigma P, which is the standard deviation, is equal to P bar into 1 minus P bar divided by N whole under the root, which would be equal to P bar value is 0.09. So we will have to put 0.09 here, okay, into 1 minus 0.09, which is equal to 0.91 divided by N, and N is 20 in each sample. Okay, so that would be equal to 0.064. Now it's time to find out the upper control limit. So upper control limit is P bar plus Z into sigma. Okay, Z is actually the 3. The value of Z is 3, which is standard deviation, which is 3. And you can put the sigma value here at 0.064. Okay, I would like to mention one important point here, that if you look into the control limits formula, so it is 3, which is Z. Okay, so P bar plus minus Z. This is the value of Z into, what is this? This is sigma, and sigma is P bar into 1 minus P bar divided by N whole under the root. Okay, so we have already determined sigma, okay, here, which is 0.064, and we will put the value of sigma here, and this is the value, and Z value is 3, so the upper control limit will be 0.282. The lower control limit is P bar minus Z into sigma. So the sigma value is same, which is 0.064, Z is 3, and P bar is 0.09. And it will give us minus 0.102. which is equal to 0. We won't show the minus or negative values in the chart. So these are the charts that we can get from by solving the example for P chart. So the value of P bar was, what was the value of P bar? The value of P bar 0.09, so it is around here 0.09 or 0.1, okay? And the value of the lower control limit was 0, okay? And the upper control limit value was 0.282, so 0.282 here. And these are, our data. So both of these charts actually represent the previous example. Let's talk about the NP chart. The NP chart is a graph of the number of defectives in a subgroup. The NP chart requires the sample size of each subgroup to be the same each time a sample is drawn. When subgroup sizes are equal, either the P or NP chart can be used. They are essentially the same chart. Some people find the NP chart easier to use because it reflects integer numbers rather than proportions. The uses for the NP chart are essentially the same as the uses for the P chart we have discussed in the previous slides. Subgroup sizes for the NP chart are normally between 50 and 100. Usually, at least 25 subgroups are used in developing the NP chart. Again, subgroup sizes must be equal. To compute the control limits on an NP chart, we can use the following formula. So the control limit for NP chart would be equal to N into P bar plus or minus, sorry, this is plus minus SNP. This is plus minus 3 SNP, okay? Plus minus 3 SNP. Okay, so N is the sample size, P bar is the average proportion defective, and SNP is the standard error of NP, which is equal to the value of SNP is equal would be the SNP is actually equal to NP bar into 1 minus NP bar divided by N all under root. So please note it here that plus is for the upper control limit, minus is for the lower control limit, and we have to write here the value 3, okay, which is not presented on the screen by mistake. So let's discuss another problem for NP chart. The statement of an example is, within the J. Kim Insurance Company of Boston, Massachusetts, management found that too many of its policies were rated incorrectly. Management directed the policy applications be reviewed for the past 24 months on a sampling basis. So you have to note 24 months. 100 policies from each month, 100 policies from each month were selected for review. As an analyst, you are asked to review the policies for correct rating. If any problem is found with the rating of a policy, it is said to be defective. So 24 months and 100 policies for each month. So 100, 100, 100, 100 till 24. And the number of policies with rating errors is this 11, 10, 12, 6. These are number of policies with errors. And its p-value is 0.11, which is 11 divided by 100 is 0.11. Number of policies with rating errors here divided by the number of policies reviewed. So the mean of P or P bar would be 0.13. It is summation of all these values divided by 24. So that will be equal to 0.13. So as you know, the formula for control limits of NP is if you want to find the upper control limit of NP chart, so that would be the formula is you know, the values are actually 100, which is n. Okay, so n into p bar. So n is, which is 100, and the value of n is 100. P bar is 0.13 plus, for upper control limit we will use the plus value, into 3 into S and P. So the value of S and P were NP bar. Okay, so this is N, which is 100, P bar is 0.13, okay, into 1 minus P bar. So the value of 1 minus P bar mean 1 minus 1 minus 0.13, so which is equal to 0.87. So its upper control limit value would be 22.88. And if you want to find the lower control limit of NP bar, so that would be 100 into 0.13 minus 3 into 100 into 1.13 into 0.87 whole under 0. So that would be equal to 2.80. So as you know, the P bar value was 13, and 22.8 is you know, how 13 is actually the value of P bar. As you can see in the previous slide, the value of P bar was 0.13 and the value of N is 100. So 100 into 0.13 is 13. Okay, so 13 is the central line, which is NP bar, and the upper control limit for NP is 22.88, you can see here, and the lower control limit is 2.80, which is here, and these are the values. So this is actually the NP chart for this particular example. Now let's discuss the C chart. C chart is a graph of the number of defects per unit. The unit must be the same metric size, such as size, height, or you can say length, volume, and so on. This means that the area of opportunity for finding defects must be the same for each unit. Several individual units are can compromise, you know, the sample, but they will be grouped as if they are one unit of a larger size. If multiple units are used, the same number of units must be in each subgroup. The control limit for the C chart are computed based on the Poisson distribution. Like other process charts, the C chart is used to detect non-random events. Non-random events in the life of a production process. Typical applications of the C chart include the number of flaws in an auto finish standard form and a number of incorrect responses on a standardized test. Again, the C chart is used when you are always inspecting the same size sample space. When the sample space is varied, such as in the inspection for flaws or different models of cars within a model family, then you will have to use the U chart in that particular case. So let's discuss the U chart and then we will move toward the C and U chart example. U chart is a graphical graphical chart, or it is a graph of the average number of defects per unit. Contrast this with the C chart, which shows the actual number of defects per standardized unit. So there's the difference between the U and C chart. The U chart is a graph of the average number of defects per unit, whereas the C chart shows the actual number of defects per standardized unit. Okay. The U chart allows for the unit sample to be different sizes, areas, heights, and so on, and allows for different numbers of units in each sample space. The uses of for the U chart are the same as the C chart. Now let's look into the formulas of U and C charts. First, look into the formula of C chart. These charts are similar, but one thing is different. Here for C chart, in the formula we use the C bar value, and in a U chart we use the U bar value. But let's discuss the formula. In C chart, if you want to find the control limit for the C chart, you have to use the formula, and that is the C bar plus minus 3 under the root C bar. C bar is actually the process average number of non-conformities, And this is the formula for U chart, which is control limit for U chart would be U bar plus minus 3 into U bar by n under the root. Please remember that we will use plus for the upper control limit and minus for the lower control limit. So here n is the average sample size, okay, where U bar represent the number of non-conformities per unit. So let's discuss an example of a C and U chart here. The statement of an example is: the J. Grout Window company makes colored glass objects for home decoration. J. Grout, the owner, has been concerned about scratches in the finish of recently made product. So there were some scratches. He noted that there were such scratches in the finish of recently made product. The company makes two products. These are the demi glass, which comes in one standard configuration, and the second one was the streakless glass, which comes in 3 similar models. Using high power magnifying glasses, the company examined 25 each of both the demi and the streakless glasses. As an analyst, you are asked to evaluate the process by determining whether the processes are stable. Assume that on average the streakless are 1.5 times the size of damas. Okay, so 1.5 times. So that's the number of items, the demi defects and streakless defects. So defects in demi were 5, 4, 6, and 2, and so on. Okay, and its sum is 144, and its C bar, which is the sum of all these values divided by 24, that would be 6. So divide by 24 or 25, and you do it yourself. Okay, add these value and divide it by 4 or 25, so you will get this value. Streakless defect mean you will have to add all these values and divide it by 24, so that would be the U bar, which is 5.83, and its U is sum, so you can add all these values and its sum would be equal to 140. So formula for C: was C bar plus minus 3 under the root C bar. So C bar value was 6. You can see here it is 6. So 6 plus minus 3 under the root 6. So its value is 13.35 for plus and 0 for minus. Okay. So 0 is for the lower control limit, which is okay. And upper control limit is 13.35 and its C bar was 6. So this is actually the C chart for you. And U chart, for U chart, U bar plus minus 3, U bar divided by N or under the root. So U bar was 5.83 and upper control limit is 11.74 and lower control limit is 0. Okay, so 0 and 7.1. These are our data that is plotted on the U chart. So these were actually the charts for the P, NP, and C and U chart for attributes. That's the end of the lecture. For more videos, please follow my YouTube and Facebook channels. The title of YouTube and Facebook channel is Learn with Wasim. Okay, and if you have any question regarding my lectures, please feel free to contact me on learnwithwasim@gmail.com. So please subscribe and like the pages and channels. Till then, thank you and bye.